Okay, so we are going to start this new topic, random variables. So based on the title, perhaps you can already get an idea what I mean by random variables. We have variables. We already learned what variables means in our first topic about when we were talking about the basic definitions. We know our variables, and we know that the values will be random. I'll show you in a bit what I mean by having the variables having random values. Okay, so as I mentioned, as already, I forgot who it was, but one of you has already guessed from the very first meeting that we will be meeting a lot of dies. We're going to be talking about dies a lot of time. Exactly. In our previous topic, we talked about probability, and we talked a lot about dies, a lot about coins. So in this case, hopefully it's really easy for you by now. So we have two die, because they're plural. And I throw my die, and I need to consider the event that the sum of both die equals 7. So in this case, we're only talking about two die, and each die has 6 possible faces. So we're not talking about a very complex combination of events, right? So it's still not that difficult for me to actually write down what possible outcomes can come up when I need to consider the sum of both die equals 7. In this case, I know that it's 1.6, 2.5, 3 and 4, and so on. So these are the possible outcomes that fulfill my event E. So in this particular event, I'm talking about the sum of both die. Just like when we were talking about the previous when we were talking about permutation and combination, the reason that we were talking about permutation and combination is because if we had a very complex event, it would be too tiresome. It would be too cumbersome for us to actually list out the possible events and count how many are there, right? In order for me to compute make the fraction of the numerator and the denominator. However, in this case, I have another argument. What if I don't even care about each possible outcome? In this event, I only need to know that the sum of both die equals 7. I do not care if it's 1 and 6, 2 or 5, or so on. This is not important to what I need to compute for this event E. So in that case, I need some way to abstract to make it a little bit more abstract and to extract exactly what I need to know only. If I don't need that step of writing down all possible outcomes, I can skip it. I don't need to consider it. And instead, I'm only interested in the 7. I'm only interested in some numerical quantity that is determined by the result. In this example, this numerical quantity that I'm interested in is the sum. So in that case, I can employ some random variables. So a random variable x is a function that assigns a number, xs, to each outcome of an experiment. So in the previous example, I'm talking about the experiment of throwing two dice, and the outcome that I'm considering is the sum of both die. So this gives me the power of abstraction. I no longer need to actually consider every single possible outcome. I just need to know what is interesting to my needs. So this is, if I write it down mathematically, random variable x, x here. So if I have a sample space, all outcomes in S, for example, like that, I have 1, 2, 3, 4, 5, 6 in this example. Instead of me actually determining, oh, like in my previous example, instead of me writing down, oh, this is 1 and 6. Oh, this is 2 and 5. I don't care. I don't need to know every possible outcome. I can map each of these outcomes to a certain number. So here I'm mapping the sample space to any real number on my real number line. I don't care about exactly what outcome it is. I assign randomly a number to each outcome. So that is where the name variable comes from. So I have each variable is my outcome in S, and I assign the number somewhat randomly or arbitrarily. So let's talk about this example here. So I'm going to try to translate the numbers, the outcomes into the numbers, just like what we did with our 2 dice and sum. So now I have a different physical object. I have a coin. I have 3 coins actually, and each coin has a possible outcome of being heads or tails when I toss it, right? So in this case, I have I denote heads as 1 and tails as 0. So I could write down all possible outcomes, 0, 0, 0, 0, 0, 1, and so on. However, I'm not actually interested in knowing what exactly comes up. I don't care if it's 0 or tails, or it's 1 or heads. I don't care if the 1 is on the first coin, the second coin, or the third coin. I only need to know the number of heads in one toss. So I have 3 coins, I toss it. I only need to know the number of heads that come up. So in this case, instead of me actually paying attention to exactly each combination 0, 0, 0, 0, 0, 1, I now assign a number. Exactly what the definition is. I assign a number from real numbers to each outcome. So in this case, I have an outcome x, 0, 0, 0, and I assign it to 0. It makes sense because in this event, there are 0 heads. And so on. So for this event, 0, 0, 1, 0, 1, 0, 1, 0, 0, I assign it to 1, the number 1. This is my sample space. This is my R number, a real number. And so on. I have 1, 1, there's 2 here, and 3. So instead of actually talking about every single outcome here, this sample space, I now only have 4 events or 4 outcomes to consider. The outcome of the random variable equaling 0, which is a random variable, was the number of occurrences of heads. The probability of my number of occurrences of heads equaling 1, and the number of heads equaling 2, and the number of heads equaling 3. Note X is the number of occurrences of heads. And based on the number of possibilities, I can also then compute the probability of each event. Oh, sorry. For example, here I know that the probability is 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So this is 1/8. This is 3/8. This is 3/8, and this is 1/8. Note some important things that come up. The sum of all probabilities equals to 1, right? And each probability is between 0 and 1. This follows all of the probability axioms that we already learned in our previous topic as well. So based on these events, however, or these variables, however, we now can define 2 different types of random variables: discrete random variables and continuous random variables. If you recall, we already learned about these two types of variables in the first topic as well. The first one is discrete, which means the value, of the random variables are countably infinite. However, that the number of values are discrete. And for the continuous one, we're talking about the function here. So it's a continuous value. It's an interval on the R number line. So it's the most important thing is that it's a real number. It doesn't really matter if it's discrete, it can be continuous as well. And this is also in line with the type of events that we can talk about. So I'm going to start first with the discrete random variables. There are two ways that we can define our discrete random variables using two different types of functions. So when we are talking about, so here we're going to do another example just to drill in the concept. So we have X is the sum of two fair die. So we're going back to the first example there. Note here, we have, since we're talking about only sum, and I defined that X is the sum of two fair die. This was my initial sample space, the one on the right here. However, when I talk about the sum, I can now define these random variable events. When the sum is 2, these are the possible outcomes, 3, and so on. And as such, when I consider the probability of each random variable occurring, I now can compute the probabilities as follows. We already did this just now when we were talking about the coins as well. And we're doing this one more time when we're talking about the two dice. And if you understood that, then you already understand the probability mass function, Pmf. So let's see the definition together first. The probability mass function is written using a small p, using small x of this random variable, which is defined as P of this X is the probability of our random variable having that value, where Px is the probability. So I'm going to go back here a sec and try to define that. So in this case, I'm going to consider this event here. I know now that the probability of my random variable having the value of 2 is 1 over, this total is 36, right? 1 over 36. This is my Pmf, which I can also write in this notation. You see? And this one follows. So if I have Px equals 3, which means probability of random variable x having the value of 3 equals 2 over 36. This can also be written in a Pmf format as small p3. So when I use the small p, it is a Pmf, and inside is the value that the random variable takes. But if I want to write it like this is the big P, it's our notation of probability that we already knew beforehand. Both are acceptable, and both are also interchangeably used in order to denote probabilities of values of random variable. So this is my probability mass. There are some conditions of this function. Since it's a function, it does have to follow some rules and has to fulfill some properties. So the first one, if x, the big X, our random variable, it must assume of one of these values, the small x's, then the probability of each small x, or the Pmf of each small x, will be between 0 and 1. I'm going to translate that into the notation that we already knew beforehand. So the probability of x equaling a value must be between 1 and 0. And if you look at it this way, you probably like, oh, well, duh, of course, because we already established in the previous topic that the probability of any event must be between 0 and 1. And that is the same that's valid for the probability of a random variable. The probability of a random variable having a certain value will also always fall between 0 and 1, which I can also use my newly learned notation, Pmf notation, to denote it. And this is the same. So this probability must be larger than 0 for all possible outcomes. And for all other values, it is equal 0. So for example, what this means is in the case of the sum, here is the probability of the sum of two dices, right? So since each of the possible outcomes equals something larger than 0, then the probability of everything else, for example, the probability of x equaling 0 will be equal to 0 to be equal to the Pmf of 0 equals 0. So every possible outcome will have a value. However, everything else will be equal to 0. The set of possible values, this is the small x, which is the possible values of the random variable, can be finite or countably infinite. And the following property must hold, that the sum of all probabilities that are valid, so this one here, must be equal to 1. This is a probability that has to hold. And this is just the detail of the third one, right? So the following property must hold due to the sum of the unions of each possible value. So I'm going to use an example here. Let's talk about a random variable x. This is just a random x, random variable, which I did not tie to any physical event. I know that my variable x, random variable x, can have the value of 1, 2, or 3. I don't know what this is, but I know that the values can be 1, 2, or 3. And we are supposedly given a Pmf of x as follows. So we know that the probability of x equaling 1 is a half, and so on. Let's do a really quick check. So this sum, this is equal to 1, right? So this is 3 over 6, 2 over 6, 1 over 6, right? If I sum them up, then this is 6 over 6 equaling 1. Okay, so we're fine. This Pmf is valid. So these are the possible outcomes. And if I just wanted to, I could also additionally define, so Px equals 0, P0 would be equal to 0, Px equals 4, or small p4 equals 0. Just a sum. And as such, how can I define the Pmf of x? I can define it as a table. And in fact, this is the most common way to show a probability mass function. I can just write a table. The first one is the possible values, and the second one is the probabilities. Sorry, this should be small p. And these are the values that it takes. We already checked this previously. It does equal 1. And I can also draw a graph of the probability mass function. Note here that since we're talking about discrete probabilities, the probability of x equaling 1 is here, and it's not valid between 1 and 2. It's only valid discretely on every single integer value that it could have. Okay, we're done with one function, and I'm going to throw you another. Now we have a cumulative distribution function, or CDF. So let's note, previously for our Pmf, we used a small p to denote it. Now we are going to use a large F to denote the cumulative distribution function. So let's see what it actually means. So you know this word, you've seen that word before. So now we need to compute a cumulative distribution function. According to the word, the word used, cumulative, so it's a cumulative probability. So no longer am I talking about exact probabilities at each exact value. However, now I'm talking about, when I say this, I say the fx means what is the probability of my random variable, large X, being less than or equal to a certain number. So in this case, I could translate this PMF into a CDF. So in this case, if I say, what is the probability, the cumulative distribution function of random variable X having a value of 2. So this is the probability of X being less than or equal to 2. From the information that I have from my PMF, which is the table on the upper right-hand side, what do you think is the value of the cumulative distribution function of 2 that I've written down here? What do you think this value should be? So I forgot to start recording, I'm sorry. So for the cumulative distribution function is everything up until, so before, until a certain value, small x. But now what if I ask you to compute the probability of a number being between 2 values? So as you can see here, if you consider a timeline, a number line like this, and if this is A and this is B, for example, based on the cumulative distribution function that we just learned about, if I talk about the probability distribution, the cumulative distribution function of A, that means I'm talking about the probability of everything up until A, right? And when I'm talking about the probability, the cumulative distribution function of B, that means I'm talking about the probability of every value up until B, right? That's what we just defined. That's what Matthew explained when he was computing the cumulative distribution function of 2. Sum up everything less than 2. In this case, sum up everything up until A, sum up everything up until B. As such, we now can compute the probability between A and B, right? So I need to compute this probability here. In other words, I can compute fxb minus fxa. So fxb is everything until B, fxa is everything until A, and the difference between the two will be the probability between A and B. Hopefully that's clear enough. Any questions? Okay, so that's our CDF. So just like our PMF, our CDF will also have some rules that it needs to follow. Oh, we have limits here. No, I don't be scared, it's fine. So the first one is that the CDF must be a monotone increasing function. This is a terminology that you should have learned in calculus. I think calculus 1, I think, but I'm not so sure right now how they divide 1 and 2. So it's monotone and it's increasing. Well, that makes a lot of sense. It's cumulative, right? So it should be increasing because you're accumulating more and more with every value. So it's a cumulative or monotone increasing function. In other words, the probability, I keep saying probability, the CDF of a value will always be less or equal than the CDF of another value, given that this value is less than this value, because it's monotone increasing. Then the limits of x approaching negative infinity is equal to 0, and approaching positive infinity is equal to 1. That basically means that we're going to start from 0 because it's cumulative, right? We start from 0, and at the end, it will add up to 1. The sum of all of the CDFs will eventually end up at 1. The largest value possible is 1. That is consistent with the property of probability that cannot have a value larger than 1, and also the axiom that says that the sum of all possible events, the sum of the probability of all possible events will be equal to 1. CDF is also right continuous. So if you recall the formal definition of limits, I believe, is the topic in calculus. When you compute the differences, then you can also prove that the limit is always right continuous, which basically means it moves to the right, and on the right-hand side or the positive side, it will always be continuous. You will not be asked to prove these properties because this is not a calculus class. So I'm going to define specifically a CDF for discrete random variables, because just now I presented the discrete random variables in two ways. We have two functions that we can use to define the discrete random variables. The first one was the Pmf, which we already went through, and the CDF. By definition, we're going to formally define the CDF is a function of value t is equal to the probability of a random variable having a value less or equal to t. In the discrete case, then in order to get the probability of x being less and equal to t, then we just sum up all of the PMFs. This is the probability equals to, which is the PMF here, of all values less and equal to t, which is exactly what Matthew explained to us in the previous example. So in this example here, we can then compute it. However, what I would like to remind you is when we're defining the cumulative distribution function, so if previously a PMF is usually displayed using a table as such, this is the PMF. The CDF is thus usually denoted as follows. So I have the cumulative distribution function of any value a. See, note here that I can use any symbol here. I can use small x, t, and whatever. And I still need to define it continuously. So it is 0 for a less than 1. It is half from 1 to 2. It is 5/6 2 to 3, and it will be equal to 1 for any a larger or equal to 3. So note that although the x or the random variable is discrete, when you display or when you define the CDF, then it should be written on with real values. And this is only valid if you are asked to write the complete cumulative distribution function. If you are asked to only compute the cumulative function of 2, then you can solve it just like what was done in the previous example. So if I were to draw the graph of this, if previously the PMF was just impulses, right? So it was a line graph for every single probability. So now we have a step function because we take some assumptions here. The CDF, if it's defined on a continuous range, in this case, it's a continuous range, then we know that for 1, the value for anything below 1, it's 0. Starting from 1, it is half until 2, and then it jumps, and then it jumps. Once again, why? Because although it is defined for a discrete random variable, a CDF must be defined on real value, or in other words, this variable there must be written in a real as a real value. So you may have noticed that there is a certain relation between Pmf and Cdf, because just now when we did our example and taking attendance, we already realized that you can compute the Cdf from the Pmf that you know. So in the case of computing Cdf from Pmf, you sum up all the Pmfs of the values lesser than that x. However, the other way is also valid. Remember, when we were computing the differences between two values, I can then also compute this. This is the Pmf of a certain value, right? I can also compute that by taking the difference between the CDF of that value minus the CDF of the value beforehand. I'm going to show you a visualization of that. So here, if I wanted to compute the probability of A, sorry, for example, and I know this is A, this is B, this is Z, then if we need to go beforehand. So the F of A would be, change colors. The F of A would be everything up until here, right? And the F of Z would be everything up until here, right? Okay, so in order for me to get this probability, which is the probability of A having that exact value, I can do this minus that, which is Z should be A minus 1. So maybe this is easier to understand. A minus 1, A plus 1, A plus 2, and so on. So I can go back and forth between my Pmf and Cdf using the relationship between the two and compute each other from each other. Okay, pause here. So there was a reason why we needed to define the CDF using a continuous real domain. So here, I need to define the CDF on a continuous real domain like that, even though the random variables were actually discrete. The reason is CDF is used by both discrete random variables and continuous random variables. Oops, sorry. So the CDF will also later be used by the continuous random variables. But although the CDF is used between the two of them, there is a function that is more unique to the continuous random variables, which is the probability density function. This is the last function that we need to know in order to define random variables. So the PDF is valid for its continuous. The PMF is valid for the discrete random variables, and the CDF is valid for both. So basically, I now want to define a probability of X being part of range B, in which B is any set of real numbers. So I'm going to translate that a little bit there. So instead of using X element of B, I think it's a little bit easier to use the limits of this range B. So I can now use P, the probability of X being between values A and B, this is my probability, will be equal to the integral of A, B. So this is a finite integral, right? So we have limits A and B, and I can take the integral of my probability density. So if you recall all of the properties of integrals from your calculus class. So basically what I'm doing is I have a graph here, right? This is my values. This is my probability density function using small f. So we use small p, big F, and small f. And fx is a graph, is a function like that. And if I want to compute the probability of my random variable having a value between here and here, I need to compute the integral of fx, right? To compute the probability of my random variable being between a certain value and another value. Or in other words, it is the area under the curve between A and B. So in order for this function f to be a valid PDF, it also needs to follow some rules, which is if I want to compute the probability, so this is my f, it should be between this and that, right? And this is the probability of this here. However, since I still need to fulfill the probability rules, such as the sum of all possible probabilities has to be equal to 1 and so on and so forth, then my x that I use must also satisfy, it should equal to 1 with limits of negative infinity to infinity, because the sum of all probabilities has to still be equal to 1, which represents the entire sample space. So the rules are still the same. I still need to fulfill that the entire sample space probability will be equal to 1. But that also has some consequences. Say that A equals B in the previous equation. So if the limits of the integral are A equal B here, this is my fx. Remember, we already established that the probability of x being between A and B is the area under the curve between A and B. If A equals B, the area under the curve is equals 0, right? So that is why the probability of a random variable being an exact value is also equal to 0. So when we're talking about continuous random variable, we assume that it's not possible for it to have an exact integer value. So it's not possible for my random variable to be equal to 2. It's not possible. It must be somewhere equal to between 2 and 3. It may be some value between 2 and 2.5, but there's no way it will be equal to a certain number. So these are the consequences of using an integral to denote your probability, right? And since we're also using an integral and a function, we now have some properties that we need to fulfill, which are, first, unlike Pmf, PDF is not a probability. The probability is the area under the curve, right? So what denotes the probability is the area under the curve or the integration. But the function f itself, sorry, I'm pointing, you cannot see what I'm pointing at. What is equal to the probability is the integral, sorry, or the area under the curve. That's the probability. But the function itself, this f itself, does not denote the probability. The integration that denotes the probability. And as such, the value of each function can be more than 1. The f itself can be equal to 1, because the important part is that when I integrate it, it cannot be more than 1. So, and as such, since the function itself can be a countably infinite set of real numbers, but the integration must be, where's my, here. The integration must be between 0 and 1, because the integration is what is equal to probability. Must be equal between 0 and 1, and so on. And these two properties is what we are going to use when we need to prove the validity of a PDF. So due to time, I'm going to skip over some questions that prove the properties of PDF. We'll do that in our class on Thursday. However, remember that the probability is an integral, right? So based on that, we have a relationship between CDF and PDF as well. Our cumulative distribution function, which is a distribution function, a cumulative distribution function of probability, random variables, being up until A. So there's no left-hand limit, right? The left-hand limit is negative infinity. So I can compute my CDF by integrating my PDF with the limits of my CDF, negative infinity to A. Or I can do the other way around. I can derive, integrate, and what's opposite of integration? Integration and derivation. So I can derive my CDF to go back to my PDF. Remember that integration is opposite, so I can use these two back and forth to move between them. So as I mentioned, I'm going to skip over these exercises. I'm going to wait until Thursday to go over these together. And I'm going to recap our three values, the three functions that we have just learned today. We have a probability mass function. The probability mass function gives you the probability of my random variable being equal to a certain value. So this probability of my random variable equaling to A, the probability of my random variable equaling to B, exactly this value. This is equal to probability mass function of B, probability mass function of A. That is my probability mass function. Next, I have a cumulative distribution function, which denotes the probability of my random variable having any value up until A. In other words, A will be equal to the probability of my random variable having any value up until A. Finally, I have my probability density function, which will give me the probability of my random variable having a value between A and B, which is computed by taking the area under the curve of a certain distribution function, which is then integrated, the integration of and these two are valid for discrete random variables, and these two are valid between continuous random variable. I can convert between these two in the context of discrete random variables, and I can also convert between these two in the context of continuous random variables. TLDR, these are the three functions that we now know we can use to denote our distributions of random variable values.